And I said, I literally did like was my child. So I literally like made it out the mud and
Okay, guys, page 27.
you were the mud.
Hey, you have a second?
Yeah.
Uh, so so far we've basically learned the majority uh, of the tests, convergence test. We've seen nth term, we've seen geometric series, we've seen p series, and then there's the yeah, p series and nth term and geometric series. Oh, and the integral test. Now, sometimes you have these series that look like it's in the same family as p series or in the same family as geometric series, but then it's added by one or subtracted by one, and it doesn't quite fit perfectly into one of the rules. So we have these comparison tests to kind of use uh, use one of the series as a anchor point, and then using that to compare. Okay, so if this is true, then this also must be true. So we have two comparison tests, and we're comparing with the known convergence rules that we've seen from the past few days. But the comparison can only work a certain way. So we have two tests here. You have the limit comparison test, and then this direct comparison test. So let's say we have a sub n and b sub n, and we know for sure that a sub n is less than or equal to b sub n. So if the series, if b sub n converges, meaning that this, if the larger series converges, then anything smaller than it is guaranteed to also converge as well. However, if the smaller series can diverge, then anything larger than it must also diverge. So our direct comparison test is a test that can use to determine the convergence of more complex for more complex series by comparing them with simpler series. And these simpler series are going to be what we're going to see with geometric series or with integral tests or with known p series. So here's just a demonstration of this, that if, let's say this b sub n converges, let's say it flattens out to some number, then anything that is less than it must also converge. Right? But we can't make a same argument, right? If something is going to converge, anything larger it may or may not converge. We don't know, right? So it's only going to be able to be a good comparison point if something is less than a conversion. Likewise, if something diverges, then anything larger than it must also diverge. Okay, we can't guarantee anything less than it will diverge because there's that gray area, right? This is our comparison point here, and we can compare for diverging. We can compare. We can prove something that is not going to pass the test, but then for converging, we'll prove something that can pass the test. I just want to give maybe an analogy of something that's, where to show that it doesn't work both ways. So let's say there's a picture of this 13-foot tall truck, and all you know is that this 13-foot tall truck will clear the tunnel. Okay. Can we guarantee that anything less than 13 foot will also clear the tunnel? Yes, right. So that's a guarantee. What if it's a 14-foot tall truck? We don't know, right? I mean, it may pass, but it's not a strong argument. It's probably close enough where it will pass, but it can only, if we have something that passes, then only less than it can be a good, a strong argument. Anything more than it is, we're kind of in a gray area. Same thing here. Let's say we have a 13-foot tall truck that will not pass. Okay, that doesn't pass, that cannot clear the tunnel. Can we guarantee that anything less than 13 foot will pass? No. Okay, we don't know. I mean, probably, right? But we don't know. This side's pretty close. But can we guarantee that anything more than 13 foot will not pass? Yes, right. Guarantee that anything, if 13 foot is not going to pass, then anything greater than 13 is also not going to pass. So that goes to show that if we're trying to prove converging, if our comparison point is a converging series, then we need something that is less than it in order for us to use this as an argument for it converging. If something diverges, if something will not pass the test, and that's our comparison point, then if we want to prove, we can prove divergence of something that's larger than that. Right? But we can't prove divergence or convergence for anything smaller because it's just not as strong of an argument. So number one, determine if the series converge or diverge. We have 1/3 plus 2 to the n. So if I can think of a simpler series, I'm thinking of this series here. And 1/2 to the n, if I rewrite it, I can make it this way. Okay. What does that look like to you? Yeah, a converging or diverging? Converging. So just by looking at this is a converging geometric series. And we're going to see if this is going to be a good fit, right? So if I add anything to the denominator, that's going to make my fraction smaller. So I think I can make this argument, right? That 1/3 plus 2 to the n is less than 1/2 to the n. So if I have a converging series, then anything less than it must also converge as well, right? If I have a truck that's going to pass, it's going to clear the tunnel, then anything less than it must also clear the tunnel as well. So we can say the series will converge by direct comparison test because we're comparing with a converging series. I'm going to use abbreviation here, direct DCT for direct comparison test. Number two, the 1/4 to the n minus 3 is, we can create a simpler series. If I just strip away that 3 there, I can make it 1/4 to the n. And this is also a geometric series, which also converges, right? Because our common ratio is less than 1. Now, the issue is that the 1/4 to the n is less than 1/4 to the n minus 3. So we have a converging series, but then this is going to be a larger, because if I subtract with the denominator, then this is going to make it, if I subtract from the denominator, it'll make my overall fraction larger. And this is not a good good way to go, right? If I have a converging series, then anything larger is that gray area. It's probably going to converge, but we really can't make that strong of an argument. So this is inconclusive. Maybe we don't have to stick with 1/4 to the n. Maybe we can stick with something that is smaller than this that we know for sure will converge, and then make this a comparison point that is smaller than our converging series. What if we compare with 1/3 to the n? Right? Will this converge? This converges, right? And we know that 1/4 to the n minus 3, that 3 is not going to make much of a difference. We know 1/4 to the n is definitely smaller than 1/3 to the n, right? Anything that's larger in the denominator will be smaller overall. And that minus 3 will just make a dent from that 4 to the n. So this is a pretty strong argument that, okay, if I'm comparing with this series, then because I can show that this is smaller than my converging series, by direct comparison tests, our series will converge. Okay, you guys want to try number 3? What did you compare it with? Yeah, 1/7 n squared is fine, or you can just do 1/n squared. We know 1/n squared is a converging p series, and 1/7n squared plus 4 is clearly going to be smaller because that 7n squared larger in the denominator means smaller overall. So that's a pretty strong argument that if my larger series converges, then anything smaller will also converge as well. Any questions with that? Now, having gone through a direct comparison test, I think for us, our tendency, our students' tendency is going to be direct comparison test is kind of like a last resort. It's a little cumbersome to set up, and I think most of us will prefer limit comparison test. But there are some there's some series that are a little bit set up kind of strange, where it doesn't quite fit any of the comparison. It doesn't usually what students do is they try limit comparison test first. If it doesn't quite fit limit comparison test, then usually last resort is direct comparison test. So let me go through limit comparison test. We'll see some examples on the next page. But here it says that if both my series are greater than 0, then we're going to find, if I can find a comparison partner with my series that I am looking at, then I can just do the limit as n approaches infinity of the two series divided by one another. It doesn't matter which one I divide by, as long as I can get a real number out of it. If my limit gives me a real number, then I know that both series will either both converge or diverge. So we're still working with a comparison partner, but we're going to find a simpler series, just like with direct comparison tests, but rather than using inequalities, we're going to think of it as a limit problem. Okay, let me show you what that looks like. So page 28, number 4. Let me zoom in a bit. Determine if the following series converge or diverge. Anytime I have like kind of like a rational function, that's usually a good fit for limit comparison test. So what we want to do is we want to quote unquote reduce the numerator and denominator to find the comparison partner. So if I just take the highest degree between numerator and denominator and just kind of strip away as many n's as I can, n squared over n to the 5th can reduce to be what? Yeah, 1 over n cubed. That's my comparison partner. Now, your comparison partner may or may not converge, but it'll work either way if it's a converging or diverging series. But it just so happens that this is a what? Converging series, okay. Here's what you have. So it doesn't matter which one we divide by each other, but we're going to use these two to see if this series can also converge as well. So we're going to do a limit as n approaches infinity. Typically, I put this over this one, but it doesn't really matter. 2n squared minus 2 over 5n to the 5th plus 3n plus 1, all over 1 over n cubed. Now, dividing by a fraction is the same thing as multiplying by its reciprocal. So I'm going to flip that n cubed up. 1 over n cubed, that is n cubed over 1. And I really only care about the highest degree. I know the lowest degree is not going to make an impact with n approaching infinity. So I get 2n to the 5th over 5n to the 5th. This is just 2/5 because if we're approaching infinity, we just compare degrees. Degrees are the same. We pull out the coefficient. 2/5, that's a real number. And so we know that limit comparison test is a good test, that we think that these two series will both share the same behavior. So this, by approaching a real number, we know this test is valid. We can use this test. And because 1 over n cubed converges, our series must also converge as well. So I use LCT as a abbreviation for limit comparison test. Yeah.
Are these abbreviations accepted by the particle?
Yeah. Typically on the College Board, they a lot of these problems kind of falls under multiple choice, so you don't have to. But for me, I just want you to at least abbreviate for me so I know what test you're referring to. Yeah.
How many more units do we have?
This is the final unit, but we're breaking this into 2 subunits. Yeah. Yeah. But we'll be done by mid-March. 1 more month, yeah. All right, number 5. If we want to do limit comparison test, what's a good comparison partner for 1 over n squared? Yeah, you can do 1 over n squared or 1 over 5n squared. I typically like to just create the simplest version possible. Okay, so try that. So what do you know about 1 over n squared? Convergence. Okay, 1 over n squared convergence. Yeah, if it's 1 over n, now let's say your comparison partner was a diverging series. You can still go through the limit comparison test. It's just that if you're comparing with the diverging series and the whole process still gives you a real number at the end, then you know that these two series will both diverge. Okay, so this is a two-way test. It can spot converging series and also spot diverging series. But if you don't get a real number in from your limit, then there's a better test available. Convergence. Either's fine.
Like, can I do this for every single? Like, even if it's the.
Oh, you mean the limit comparison test?
Yeah.
You can, yes, you can if your limit gets you to a real number. But if your limit gets you to infinity, then this breaks down. This would not be a good justification for your result. But yeah, if it's tedious, as long as you can get a number to show up, then you can do limit comparison test every time.
I don't know how to explain it.
Then you gotta
I
find a different method.
But I did know.
Yeah, we find that. It depends on the problem, right?
Yeah, you guys watch it.
One over n is probably 1/2 that virtually.
That's not.
Number 6. Number 6, what's a good comparison partner? 1 over n to the 1/2. 1 over square root of n. And what do you know about 1 over n to the 1/2? Diverges, right? This is p series, right? P series will diverge if your p value is less than or equal to 1. So we're playing with a diverging comparison partner. So I like to jump to this step sometimes where if I know I'm dividing by something, I can just multiply by its reciprocal and I can kind of just save a previous step rather than have to write out a complex fraction and then flipping it. I'm just going to just flip it right at the beginning here. And this will give me a real number because my degrees are the same. I'm just getting, sorry, it really should be 1 over square root of 3. But that's still a real number. So because our comparison partner diverges and we get a real number, our series will also diverge. All right, try number 7. Number 8's a little strange, so I'll go over number 8 with you, but I think you can try number 7. That's n. Sorry, it's not very clear. That's n cubed above, and that's n to the 5th below. N cubed above and n to the 5th below. Yeah, limit comparison test has a certain look to it. If it kind of looks like a rational function, that's usually a good indication. Okay, I think limit comparison test, they're trying to get us to use that.
Main fraction, and then you do the some part and then you just multiply those, but you don't put the limit as an approaches infinity.
I want to see that limit as n approaches infinity because that's what is showing us that we can get to that number there. Yeah. So do show that limit notation. You can skip the dividing by the complex fraction, but I do want to see your limit notation. Correct. Okay, what's your comparison partner for number 7? 1 over n squared. It's a converging series. And I'm getting a real number from my limit evaluation. So therefore, my series, this test stands. And we can use the test to show the two series both converge. Okay, let me go over number 8. Number 8, I'm going to play with the form a little bit here. If I strip away that 2 and just look at that n times 3 to the n over 4n cubed, I can't get everything to clean up. I can strip away that 4 is not going to mean much. I'm also going to take away one of the n's here. So I can say 3 to the n over n squared is a good reduced version of this, right? If I strip away the +2, if I strip away the 4 and just keep the main portion of it. So are you good with getting this all the way down to this simpler version? Now, what do you know about 3 to the n over n squared, just from previous knowledge? Converge or diverge? By the what test? Okay, this we can do n-term test. Right, if the limit as n approaches infinity of my rule of sequence approaches infinity, we know this has no chance of converging, right? This is a diverging series. My numerator is moving at a faster rate than my denominator. Exponential grows faster than the quadratic. So n-term test tells us this is a diverging series. So this can be a good comparison partner. We know this for sure is a diverging series. Now we can go through our limit process here. Okay, dividing by a fraction is the same thing as multiplying by the reciprocal. So I'm just going to take my series and multiply it by the reciprocal of my comparison partner. My degrees match because I'm able to cancel out the 3 to the n. I can ignore the +2. That gives me 1/4. Hey, what's your comparison partner for number 9? Yeah, so n over n to the 3 halves, reduce it to be 1 over n to the 1/2. That's a diverging P series. I can show that the limit gives me a real number, so we have a valid test to show that both series must diverge. Or our comparison partner diverges, so our series also diverges. Okay, we're just going to work through our packets, their homework, page 19 through 29. Okay. We're going to be able to finish all of our topics for the first half of this unit by Friday, and then we'll just spend the next 2 weeks reviewing. But next week, we will have a quiz, but the quiz will just be over before this section. Okay, so before comparison test. So just geometric series, nth term, integral test, phi series. Oh, I still need to show you telescoping series, but I'll do that. I'll probably show that to you next Wednesday. It's easy. We can do that real quick. All right, go get your phones. I gotta go.